bit more information about kind of scope designs and things that we have now. These, this is borescope info, but it's really should be scope tip info, because this could apply to video scopes. It could apply to fiber scopes as well. But the different types of tips. So as I showed you here, we have a bottoming or 0-degree scope. We also have a 90-degree or right angle scope. There are also what's called forward oblique. So, instead of looking straight up, it would be tilted forward a bit, center of view. You can have retrospective, which is where it looks back towards the eyepiece. And then you have what's called a circumferential or circumference scope. These were early, before when lenses and prisms were really expensive to make a bottoming scope. They primarily relied on mirrors. And it works like a Dobson telescope, if you're familiar with those. But you're looking down the center, and there's actually a mirror. Hard to see if this will work. There's actually a mirror kind of back in this area. So you look at this plate, you see kind of a dead spot in the middle where it looks up, and then you also get like a ring of a forward view. So you have like a donut-shaped view forward with a circular view looking up. Kind of an interesting combo. You can actually get these scopes that we just got. You can get a version of this that has 2 cameras on the end, where it does a split screen, and it's got a forward-looking and a side-looking camera on the same tip, a 90-degree and a 0-degree. And so, those are available too. It does a split screen. I just wanted the big screen since it articulates 180 degrees. For our purposes, I thought that would be a little more useful and have just the one bigger image. But there's all kinds of different combinations. The other thing you can have, I talked about where some of these other NDT processes we're going to do use things that like fluorescent inspections. You can get scopes that instead of having a normal visible light bulb or LED in the end, they have like a black light bulb in the end. And so you can do inspections in different, in a different wavelength of light, or with different kinds of penetrance and things like that. Looking at borescopes and video scopes, fiber scopes, particularly borescopes and fiber scopes, we do have to keep in mind a few things, and that is that your view can be distorted. So anything that uses lenses, prisms, or mirrors, curved mirrors, is going to have what's called a focal length or a focal point. And that is the distance from that lens or mirror where objects are the same size, appear correct proportionally, size-wise. You've probably, most if not all of you, have experienced this in some form or another. Anyone know where you've seen this kind of an effect taking place? What's that? In your car? What's in your car? You got your side mirrors. What do your side mirrors say? Objects in mirror may appear closer than objects in mirror are closer than they appear, right? So that means it's making the object look smaller, right? So that is when you're further away. So if we look at this diagram here, this lens or prism or mirror has a focal length of 2 inches. You can see at 2 inches, the image size is a 1-to-1. Okay? Again, it can apply to a curved mirror. It can apply to a lens as well. Anything closer than 2 inches, as you get between the mirror or the lens and the focal point, if you get halfway, things look double in size. If you get 3/4 of the way there, it gets to 4 times the size. If you get 7/8 of the way, it would look 8 times its size. Okay? Going the other direction, if you go twice the distance, so if you go from 2 to 4 inches, objects are going to look half the size. So your focal point on your mirrors for your car, for instance, is typically closer than the vehicles behind you. So anything that's past that mirror focal point, that's why those objects look smaller, why they look further away in your mirror. The reason that it's done that way, one is so that your mirror's in focus, the other is to give you a wider field of view, so you can see more behind you than you would if it was just a flat mirror. Okay. So we have to keep that in mind when we're looking at things. This can distort the way things appear when we're looking through a scope. And so we have to keep that in mind. I'll show some other examples that kind of give that. A few things here. I talked about the different terms. I've just got these in here so you have them if you look at the slides. Objective distance is the distance from the objective lens to the object. Okay, that kind of goes back to here. So if you have an objective distance of 2 inches, it's at the focal point. Objective lens, I mentioned, is the lens closest to the object. Overall length, and the end we saw in that image. Relay lenses are inside the scope, moving it from end to end. Resolution, ability of an optical system to distinguish individual points of an object. What is the resolution of this scope that uses lenses and mirrors and prisms? What's the resolution of this? So theoretically, this has an unlimited resolution, right? Because we're just taking that image and relaying it with, if you have optically pure items, which every optic has some form of error in it, you can get on the, so what limits our resolution when looking through, say, a scope like this? Dust will interfere, contaminants. Say you had perfect lenses, dust-free, your eye is going to be, right? What can you discern with your eye while you're looking through the scope? That's your resolution limit. On something like the fiber scope is not a single fiber, it's a bundle of fibers. So when you look through, I don't think anyone pulled the fiber scope out, but when you look through the fiber scope, take a look through it. When you look at the image, it's not a single image. It's actually a bunch of circles. It almost looks like a honeycomb. And that's the individual fiber. So that can cause some resolution loss because you do have little black spaces between, each of those fibers. There's a tiny little gap there. And as I mentioned here, you'll see it has some dead fibers too. What about in a video scope? What's your resolution? The what? Pixel resolution from the camera. This one here, older, the Olympus, has a 640 by 480 resolution. These ones we got the other day have a 1080 resolution. It's the same resolution as a high definition screen. Now, the screen on here, by the way, is not 1080. That's the size, that's the pixel density, the resolution of the camera. To see the full resolution, you have to take the pictures off of here and put them onto like your computer or something. Okay, so just know that the display and the camera can have a different resolution from one another. That also applies when we get to thermal cameras, the resolution of the thermal chip versus the resolution of the screen on the camera. Any kind of camera, you can have 2 different resolutions. You probably will be able to see more. If you pull a picture off this borescope, put it on your computer and blow it up, you'll be able to see more than trying to look at it on that screen that's only 3 to 5 inches around. Rigid borescopes, we saw what those are. The sheathing is the outer covering. It can be a metal. This is just a solid metal sheathing. You saw the braided sheathings on the various flexible scopes. Visual acuity, that's what I was getting at with the scopes. Visual acuity is your ability to perceive things. How good is your eyesight? NDT, you don't have to have perfect eyesight, but you got to have pretty good eyesight, or you got to be able to correct it, right? Wear glasses, contacts, or have good enough eyesight that, I don't have perfect eyesight. Mine was good enough. I wouldn't have to wear glasses or any kind of corrective lenses when I was doing it, but I don't have perfect vision by any means. Depth of focus. So I talked about the focal point being a certain distance from a lens. You can make lenses and mirrors where the depth of focus is such that that's how far in front of or behind that focal point objects will still be in relatively good focus. As soon as you start moving from the focal point, you start to get a little bit of blurring going on. Right? You've all seen pictures, someone up close, their face, and the background way in the background is blurry, right? The face is at the focal point, the background is blurry. Lenses, like your camera on your phone, have a very wide depth of focus because they don't have, it's a fixed lens that, people want to take pictures up close, they want to take pictures further away. Now, newer phones sometimes have 2 or 3 lenses, right, for different, you want something up close, something further away. But if you just have a single fixed lens, like a borescope, right, it's going to have a depth of focus where things are going to be ideally in focus. And if you move further or closer than that, it's not going to be as perfect focus, but it's good enough for what we're doing. And that's where, when we saw the video on the measurement scope, right, it talked about how far are you from what you're looking at, whether you get a green reading or a yellow reading. That's because if they're too far away, if you're further away than that depth of focus, it can, that fuzziness that gets in there can make it where the measurements aren't reliable. It can also happen if you get too close to something. If you put your fingers right in front of your face, you probably can't focus and see the lines in your fingers. If you put them out, arm's length, I can see the swirly lines in my fingers. If I put them too far away, it's harder to do it. Your eyes can adapt, though, a little bit to that. They have a variable depth of field. And nicer cameras have a variable depth of field. The diopter adjustment can correct for that a little bit, but that's, again, that little focus ring on these primarily is to adjust for your eye, to match the lenses to your eye rather than to focus the objective lens. And I didn't mention the fiberscope does have that as well. On the fiberscope, it's a little stiff, but there is a focal ring there. Diopter correction, that's this thing I just mentioned for the eyepiece. Fiber optics, we looked at the different cables. Fiber optics can come in two types, what's called a coherent array and a random array. So fiber optics, it's a bunch of glass or plastic fibers. Okay, glass gives you better resolution. Plastic, is usually cheaper and more durable, but you get better image transmission with glass fibers, pure glass. Think of it like spaghetti. A coherent array is uncooked spaghetti. If you grab a bundle of spaghetti and hold them all together, the stick of spaghetti on top at the end closest to you is probably going to be the stick of spaghetti at the end furthest to you that's on top. And the one on the bottom is going to be on the bottom, the one on the left is going to be on the left, the one on the right is going to be on the right. So if you were looking at an image, that image that you pick up over here would look good, would look correct to you at the eyepiece end. A random array would be like cooked spaghetti that you had kind of straightened out and tried to put back into a bundle, right? The piece that starts at the top closest to you may not be at the top at the far end, right? You can straighten them out relatively, but they're not going to be in the exact same position relative to one another at one end than they are at the other. And so that is useful for transmitting light where we don't care what the image looks like, but it's absolute garbage for transmitting an image because it would scramble the image by the time it gets back to your eye. So back in the day, random array fiber optics were a lot cheaper and easier to make because you didn't have to be as careful. The quality control didn't have to be there as a coherent array, whereas the coherent arrays were more expensive. So they would use a coherent array fiber optic for the visible, the image you're trying to transmit, and they might use a random array to make the light transmission bundle. Nowadays, manufacturing of this kind of stuff has gotten so cheap, you really don't see too many random array fiber optics out there anymore. They've pretty much gone, it's not that much harder to make a coherent array. And it's not really any more expensive. So flexible borescope, is known as a fiberscope. Focusing, focus stuff. Image is the reproduction of an object with light, and magnification is a ratio of sizes. Okay? So those are kind of the terms we have. Next. Okay.